Good afternoon, Professor Wang Zhonglin, Professor Wang Zhongkai, and Professor Chen Qingchen. Colleagues, ladies and gentlemen, welcome to this pair distinguished lecture series. You know that the pair organize this lecture series, and we often invite very outstanding academics to give lectures. And today we are very honored to have Professor Wang Zhonglin from Chinese Academy of Sciences to be here. And now I would like to invite Professor Wang Zhongkai, our Associate Vice President for Research, to give an introduction of our speaker. Professor Wang, please.
Okay, colleagues, students, it's my great pleasure to introduce Professor Zhonglin Wang, actually my collaborator. Let me briefly share a very, very unique story. We have a collaboration paper, and during our paper in the final stage, one referee asked, because in the acknowledgement, we usually use initial, right? One referee asked, please clearly mention VW, which VW is Professor Zhonglin Wang, which VW is Professor Wang Zhongkai. Okay, so I really have the pleasure, honor, privilege to collaborate with Professor Zhonglin Wang and also have the theme VW. I think PolyU, one advantage of PolyU is we just walk 5 minutes to the avenue of star. But today, we don't have to walk. Here, we will really enjoy the star of science, Professor Zhonglin Wang. I think today is the coldest day in Hong Kong, but probably the hottest day in terms of scientific exchange. I didn't feel well today because I suffer from stomach problem, so I will not introduce Professor Zhonglin Wang, but instead, I want the audience to introduce Professor Zhonglin Wang. For that, I prepare some gift, from graduate school. If you can introduce Professor Zhonglin Wang, use a very simple, especially use sufficient and necessary condition correctly, I will give you the award. Whether your answer is correct, depends on Professor Zhonglin Wang's judgment. Okay. So who can volunteer to introduce Professor Zhonglin Wang? For example, Professor Zhonglin Wang is blah, blah, blah. That one should be very accurate, scientifically accurate. Okay, anyone want to volunteer? Okay.
Okay. Well, I didn't read your resume very well, but I know that you are the #1 in the world in terms of scientific citation numbers, right? This is probably, I think the audience knows, we have a list of 2% of the top scientists composed by the Stanford University. And Professor Wang has been on the top list for like the last 7 or 8 years. This is an unbelievable achievement.
So you're correct, right? Okay. Anyone? I still have one gift, okay? Okay. Oh, good.
I'm Zicheng Zhu, just joined the PolyU 2 months ago. I have a great honor because Professor Wang is falling a fellow of Royal Academy of Engineering. I'm a fellow of Royal Academy of Engineering as well. And also, Professor Wang is the recipient of Global Energy Prize. And I'm the one, I think, one year after you. Okay, thank you. It's a great honor to attend your seminar.
Okay, thank you. Okay. Great. With that, I think we can leave the room to Professor Zhonglin Wang. Let's welcome Professor Zhonglin Wang to deliver the talk, right? Okay.
Well, first, it's a distinguished honor for me to give this distinguished lecture. Thanks to Professor Zhongkai Wang, Professor Chen, and all the distinguished audience today. And I'm very happy to be on campus of Hong Kong PolyU again. Last year I was here twice, and today is a special journey for me to stand in front of you, give a full presentation on what we have doing. And today, especially some of my graduate students, they are doing postdoc in several universities in Hong Kong. They are here too, and they are the ones, part of the ones who made a contribution to my presentation. And as you can see that I was a professor at Georgia Tech for 25 years, and I retired 2020, and I joined Beijing Institute Nanosystem full time. In fact, this institute I founded more than 13 years ago, and it has grown really well. Okay, today when you talk about triboelectricity, a lot of us says, I know it very well. And of course, this phenomenon has been played important role in our human civilization, especially early days when we realized how to make fire, how to make transportation run smoothly, especially through the triboelectricity. People learn about electricity. And this is the beginning. We studied static electricity. And it had been 2,600 years ago since the first record of triboelectricity. And the fourth important contribution to us is you can see why the flowing water will not be deteriorate. You wondering about this phenomenon. Do you understand the physics and the chemistry behind why the flowing water will not be deteriorate? Why so? We know the phenomenon, but there's a chemistry behind it. I will talk to you about today. It's just because this nature move provide us with clean water to make sure all the human and the animals on Earth grow in health. Okay, so I will talk about the chemistry just a second. All right. So if you talk about this one, it has made a major contribution to human civilization. Of course, people have studied this for decades, centuries, and because it's one of the earliest recorded phenomena, until the last 20 years or so, it has been very extensively studied because it used to be regarded as a negative effect. So cause fire, cause other things. So people said, well, we knew it, but we don't want to start this in the details for that. So in the last 20 years, a lot of groups studied this in depth, and think especially like the audience here in Professor Zhang Wang's group and Professor Hao Jianhua's group, they did a study on this one because it brings new technology and sense to us. So my presentation today, several parts. The first part is the fundamental science. So if you do this one fundamental, you talk about what is the basic contribution to science, why we are interested in this today. Okay. First one is the energy. When you talk about energy is a challenge for us now, it's going to change for us forever, because we need more energy, especially we have the major power, also we have the distributed power. So the future will be the integration of a major power grid with distributed energy. Such largely distributed, low density, but the quantity is very large. We call high-entropy energy because it's kind of random, unpredictable, right? So therefore, the world going to be run by all kinds of means on energy for us. So how do we generate those powers? How do we make the world sustainable? It's always a challenge for us. Okay, so I personally started it with our team on the piezoelectric nano generator on 2006. So this is 20 years ago. And 2012, we made a surprise discovery. We use triboelectricity can be a power generator. You know that triboelectricity is a phenomena. We used to say triboelectric discharge, but now it's triboelectric power. That's a different thing. So how is it working? It's making two dielectric material, one contact with the other one. So you cause the charge on the surfaces. And if you use the external force to bring to take the two parts, so you generate a displacement current, which drives the electron to flow between two electrodes you give out power. So this was the beginning of this work. Okay, up to now. So why is different from the 200-year-old technology we have known so well? We knew use electromagnetic induction for power generation. This was first introduced by 1831 by Faraday. And this is the major thing we use today. Use magnets and coil. Its output voltage and current is proportional to frequency respectively. So the power is F to the square. That means we need to run this power generator at a high pace. If you run at a slow pace, the output is very slow, very low. So it works best at high frequency. But in our daily life, we have lots of slow motions, especially related to human. So we use triboelectricity. It's a high voltage, low current. The electromagnetic generator have a high current but low voltage, both just opposite. Use different materials. TNG, the English abbreviation, triboelectric nanogenerator, TNG. It's use polymer materials, use contact electrification as the mechanism. Electromagnetic induction use Faraday's law, use electromagnetic induction as the driving mechanism. So the fundamental mechanism change, the material system change, the output characteristic change, and of course will result in a diversity of applications, right? So this is the basic. So if you look at this one in detail, if you run at low frequency, the output of TNG is 10 times of the EMG at low frequency, okay? If you run a low amplitude, that means the amplitude is very small, the output of TNG is 8 times of EMG. So if you can find a domain in which that the performance of TNG is far more superior than the EMG, okay? So in our daily life, we have a lot of actions moving. So we want to convert either moving into electric power or we want to convert it into a sensor. So we need both, okay? Most distinguish this one from other effects such as piezoelectric effect, other is the diversity choice of materials. Literally any material you'll be able to utilize for TNG. You can use oxide materials, you can use polymer materials, unlimited availability of materials choice. That means unlimited field of applications. So that's the key difference from other effect. If you work on a solar cell, I use a silicon or Prof solar cell. Either one, you have to use a specific material system. Or lithium battery, you have this specific material system. But for TNG, it's a broad range of choice. That's why around the globe, so many people are interested in that. And particularly, the domain which you can apply it is complements to EMG. You can work on low frequency, low amplitude. It's just fit today's society need for Internet of Things, for artificial intelligence. Just fit what we are today, okay? So this is the materials choice for that. And let me show you why it's so broad impact. And then as Professor Chen asked me, how come you become the #1 in world impact for science? So here is the story. This is, we did a recent study on the papers published with the TNG. This is the number of papers. Last year published 2,777 papers for that. And 14,000 papers totally published, and 22,000 scientists, authors, across 4,300 units in over 100 countries and regions who are engaging in this research right now. So this number of papers is increasing. Also, the number of authors, you can see, just last year, almost 10,000 authors. So increased dramatically around the globe, over 100 countries and regions for that. And the insert is number of affiliations. How many affiliations they're doing this one, right? That's one. So this is, we just did a literature survey, find that. And there was a paper published by ACS Energy later. The title was, how many reviews do we need? The title by the editor. You find it interesting is that they find the publication in 2023 to 24 in lithium battery is 38,000 papers. In the Prof solar cell, solar cell is 11,000 papers. In TNG is 4,500, okay? It's 11% of the lithium battery papers, almost 40% Prof solar cell papers. So this field is fastly growing and also limited potential, okay? Now, when I talk about this one, you say, what's the application? You talk about that. Before I talk about application, I just show you there's a broad range of application for wearable electronics, medical sciences, infrastructure monitoring, safety, as well security, as smart fabric, a lot of things for that. And I will talk to you to first one, contribution to fundamental science, all right? Because it's only if you have something new in science, that means the technology application will be unlimited, right? First one, impact of chemistry. And this is started from a video we took. This was 2014, and that time we used to study liquid and solid quantification. We find that we can have power generation, and we wrote the paper, and 2020, Professor Wang wrote another beautiful paper published in Nature on the liquid, so much more improved performance. This started work on liquid solid quantum electrification. Today, a lot of chemistry being built around this. So as you see, this is the beginning study, fundamental of liquid and solid. Is there any charge transfer? How come a liquid droplet become charged? What kind of charge are they? Okay, so this is the beginning of the 2014, published the first paper on that. This goes to the fundamental of chemistry, so-called electric double layer. If you work on a supercapacitor, on energy storage, you must use EDL. Okay, this is the fundamental. So when it says when a liquid contact with a solid, a layer of ion being absorbed on the surfaces. So our question at the beginning, are any electron transfer? Why only ion absorption? Is this the full model? After we studied, we found this is not the full model, but you read a lot in textbook about that. So how do we do the study on this one? Yeah, you see, if the water floating fountain here, you see with the charged plastic is attract with each other because the floating water have charges in that. So what kind of charge is this? So we study in detail here. Is that we use a silicon oxide, use thermal annealing, get rid of surface charge. Then you drop a single drop of water on that, you evaporate. Then you measure the charge on the surface. It suddenly drops from 0 to minus 800 microcoulomb per meter square. Charged, negative charged. Then if you keep this at a stable, at room temperature, it decays for a long time. If you heat up at 393 Kelvin, it drops like that, okay? But never reaches 0. If you heat temperatures 433 Kelvin, it decays like that. So this residual charge are the ions absorbed on the surface. The ones you got rid of by thermal effect, called thermiotic emission, are the electrons. So you can quantify how many electron transfer, how many ion transfer. So this is the first droplet. If you repeat this one for the second droplet, after you can rebuild the charge again, then after dry, you heat up to reach new saturation. Since this is more ion on the surface, the third droplet, fourth droplet, you reach ion surface. So at the very beginning, if you have no temperature fluctuation, you have both electron and ion transfer. So this indicates us the charge have both ion and electrons. But the electron transfer is much faster. Why? It only took a femtosecond layer between the electron transfer from liquid to solid. But ion absorption to the surface take a micro or even millisecond. So much slower, okay? So this is the beginning of our study, liquid and solid. Then you say, well, how come water lose electron? Is this possible? We don't believe this is possible. But a few years ago, this beautiful study, they used time-resolved ultra-fast X-ray laser. They find water can become water ion. The only thing is that it's lifetime in a picosecond scale, during which the water ion combined with one molecule become a radical and another group. So this water lose one electron is possible. So water is not just a solution, diluted things. It participates in chemical reaction. We did not realize that before. Let me tell you how come, okay? So this just shows electron transfer involved in this one. And as a result, if you have a virgin surface of solid and a liquid put on that, first one, electron transfer occur very fast. Femtosecond, finish, okay? Then the ion sorption migrate to the surface to form a layer of ions. The below here is a layer of electrons and some ions here. So this means what? The formation of electric double layer have two type charge, electron and ions. We used to only believe it's ions. Okay, so number one. Number two, the formation of electric double layer is a result of contact electrification or triboelectrification. In a solid, we normally call triboelectrification, but a liquid or solid we call contact electrification, most scientific. So this is what? This is the liquid and solid form electric double layer. And a lot more study you can go beyond that. As a result, then you'll be able to study how if you have a droplet float down a ray of electrode, you can map the charge transfer between the water and the surface. How can you do that? You made a ray of TNG. So each yellow dot is an electrode. So you make 433 as a ray. This array, so when the liquid flow down here, from here, you can measure the charge transfer. So therefore, as you see from here, you can see the droplet flow down here, you'll be able to map the charge quantitatively. And you can heat up, you can see how many electrons get rid of. So this provides a new probe for study, TNG provide as a probe for study charge transfer liquid and solid interfaces. And I think this is important for chemistry, right? Then why the floating water will not be deteriorated? Okay? 就流水不腐. We did the experiment here. Okay, this is the experiment. We have a little flux here. This without FEP particle. FEP particle is a triboelectric material, and this is with the FEP particle. Then you apply ultrasonic wave. Then you see the ones with the FEP particle with the methanol orange degrade very quickly. This does not happen. So it means the FEP is not catalysis. But why the catalysis occurs? This is a new process, is this. Two steps. First one, if you have the water and FeP particle in contact at the very beginning, electron transfer occurs. This only takes a femtosecond scale. The water becomes water ion, but this water ion lifetime is picosecond scale. It combines with one molecule, become a group and a radical. And this radical forms a peroxide oxide, so it's H2O2, and degrade organic pollution in a solution. So this is the first step. The second step is that you apply ultrasonic wave, and these electrons kick it back by phonon excitation, combined with the oxygen in the water, and this is negatively charged oxygen. It combined with this group. You see, this group is coming here, and recovers one molecule and a radical. And this radical eventually degraded organic pollution here. So this water molecule go in, water molecule recover, form a full cycle. This is called contact electrocatalysis. We first found this one in 2022. The first paper published in Nature Communication reported these things. Now there's a lot of group studies, CEC, contact electrocatalysis. Because a lot of materials, as long as you have physical motion, catalysis occurs. You say we have photocatalysis, we have electric catalysis. If we don't have photon, we don't have electric. Does the catalysis occurs? Yes, if you have motion. You have motion, it occurs. So this is why the evolution of in our nature, a lot of things take time because it is the motion-driven catalytic process called CEC, and this is now being widely studied for that. Okay, so this is the chemistry. They say, is ultrasonic wave needed? The answer is not the only means. You can use ball milling, any physical motion, you can excite this kind of CEC process. And using this process, we have recovered precious metals, recovered lithium ion battery materials, and we also do a lot of food processing and many other things. So you can see there's a lot of work being done around the globe in this field. So this started a new interesting field in the chemistry, right? And also recently studied a lot of use called microdroplets. The magic microdroplet is the charge transfer. It's due to contact electrification. Number two, the droplet becomes smaller, the surface charge density becomes larger, so the electric field on the surface becomes larger. That can cause some chemical reaction. But what causes this electric field is the charge transfer on a liquid droplet. So you studied it. When you look at fundamentally, it's basically contact electrification is the basic mechanism for that. All right. So this is, and then now you understand in our nature why the floating water will not deteriorate, and this is the nature of us clean water. Right. Okay. So this is for the chemistry side. Now let's talk a little about physics. Physics, first one, we knew contact electrification for a long time, but why it happened? It's always people doing tribology study, this is material species transfer. People doing chemistry, they say ion transfer. People do physics, says electron transfer. Which one is which? They have debated for many years. But in fact, we find both are electron transfer and ion transfer. Depends the environment you involve in. The basic of involve, we find use EF measurement. If you two materials, two material contact only occurs when the distance between at the special region be shorter than the bonding length. Why? We measure that, find you have in the repulsive region. That means what? The two atoms has to be so close, they have a strong overlap in the electron wave function. Only in this one, the charge transfer occurs. So as a result, we propose this potential well overlapping model. So when your two atoms become so close, the barrier between the two will be reduced. So you have a strong overlap of electron cloud. As a result, you can have a charge transfer from one atom to the next one. So it's transfer and a transition. I will show you the evidence support this one in next view graph. Because this, you have a transfer and transition, you're going to have a photon emission as this transition. And we observe that experimentally. So therefore, if the charge occurs already, when you separate them, this negative charge, this positive charge, but thermodynamic emission eventually reach equilibrium. So that's the nature, it's curve for that. Okay, so now let's look at the evidence to support this right here. Okay, and in order to do this one, we build a system called use a FEP film and quartz film. So make a contact in a vacuum. So we observe photon emissions, but the photon emission you have to be careful. One is the arc discharge due to the air around it. The other one is truly atomic spectrum emission. And we do find the line width very narrow, 1 nanometer or so. And the position of those lines fits well to the interatomic orbit transitions, as we expected. So after careful study of this case, we find this does occur. The electron transfer can transfer to one atom, a lower case. You give the emission from this atom. This is the number one pass. Number two pass is this charge can transfer to the neighborhood and drop down. And this also can occur. So we observe both photon emissions as a result of contact electrification. It's an indicator. Truly, at the very beginning, is electron transfer is dominant. It's dominant. Okay, so this provides fundamental, but our understanding in the physics for that. The second one is that we do TNG for over 10 years. Can we quantify the output? Can we make predictions? Then I started work on a theory for that. If you work on a major power here, the theory is well established. However, if you look at what we do here is not established, because what is that we have the medium motion around us, then cause problem. This set of equations called Maxwell equations, which was developed 150 years ago, okay? But this set of equations derived on the condition, assume stationary boundary and medium. That means nothing move, only electromagnetic wave back and forth, okay? But that sentence is rarely written in a textbook, so a lot of us don't know about that. And we just carry on as we do. So displacement current is different from conduction current. Displacement current is not an electric current of moving charge, but a time-varying electric field. That means time-varying electric field plus medium motion. Okay. Now, if you have motion here, now in our system here, we have the medium moving. So this changeable boundary condition, changeable medium configuration during the process cannot be easily adopted in those equations here. So therefore, we have to introduce the additional term which due to medium motion in the equation. And this is a long story, and I don't have the time to cover the how do we derive equation, but I'll just show you the results. So if you work on power industry, you just use this Lenz's law. It's called the changing rate of magnetic flux through an open surface is the electromotive force. And this have two terms. One term is this point is not as nice as I expected. Okay, sorry. All right, you don't have cursor, do you? Okay. The first one is the field change. You see this the field change. The second one is the motion. I don't need to use this one. Is the motion. I just use my words. Okay, so you work on that. That's fine. However, if you work on electromagnetic field on right hand side, which is what? Which is you do the electromagnetic wave. Nothing move in the medium, nothing move, but magnetic wave go back and forth. These two set of theories were derived on a different assumption. On the Lenz's law, you must have medium motion. On the Maxwell equations, no medium motion. So how can you merge the two together? You have additional term. The additional term appears right in the equation here. Okay, maybe battery low. Oh, sorry. Here, right. Okay. So right. That appears. Is a non-linear term. Non-linear term. So the introduced non-linear term, do you have experimental proof for that one? Very recently, we have done an experiment. Let me show you this non-linear term here. Let me first show you, this is a Maxwell equation itself is a linear equation. That means what? If you have excitation source, the frequency is omega. The output electromagnetic wave is also omega. You can't have 2 omega, 3 omega. You can for linear the system for materials here. However, we recently done experiment shows different. Let me show you. This was a beginning. We have a magnetic disk rotated, a disk rotated in a magnetic field. Besides the rotation frequency give us a radiation right here. We have additional term. This is a metal disk. Is have the turbulent. This have the current induction with the disk. Okay, and this current give you more addition to the electromagnetic wave. So this is the first paper we published. Most recently, we have do another study experiment. I think the result is really beautiful. We use a dielectric disk, so rotating. If the rotation, this surface have a charge, so the current goes like that. So the current goes like that. You suppose have a electromagnetic radiation, the frequency same as the rotation of the disk, right? That's what you expected. However, if you look at here, beside the way we see, we have, if the frequency is 13, we have 26, 39, twice, 3 times, 4 times. Around 50 is the frequency of the AC power, okay, for measurement. So this multiple harmonics appears. The appearance of multiple harmonics is a result of this nonlinear term right here. Otherwise, you cannot explain. You cannot explain it. So this set experiment proof the nonlinear term we introduced is truly valid, is correct. You just did not do the experiment before. If you do the experiment carefully near the power generator, you have multi-harmonics. You measure it, okay? It's also caused noise for electronic. So therefore, a lot of things we just used to, people say, yeah, we get used to this one, but double thinking. Used to, a lot of things have assumption behind. Is this assumption valid here or not? So we have to rethink about that. So this is just a recent result which we received. So the appearance of multiple harmonics is a support for this term. Okay. The second data is that if you have a disk running like that, you expect the magnetic field goes like that. If the disk run like that, you expect the magnetic field to go like that. You anticipate if the rotation velocity reverses, you anticipate the field reverse, right? That's normal. However, we find those harmonics, they do not exactly follow what I expected. If you, the first harmonic, third harmonic, that's the odd order, 1, 3, 5, you have a 180-degree reverse in the field, as expected. However, you have the second harmonic, fourth, sixth, you do not. This cannot be explained by classical electrodynamics unless you introduce the additional term we introduced. Because why? Is have V. If you have a V reverses, this preserve the sign. So second harmonic, you not have no time, no reversal in time here, because of V multiply, negative multiply negative positive. So therefore, this phase change give another support of additional term, introduce Maxwell equation for that. We'll do a lot more result now. A lot of things we did not understand previously is because we did not do the experiment as what we're supposed to do. We only look far field electromagnetic radiation, but if you near the object, you see those things. Okay, so I just spent a little time for that one, and now become the fun part. Goes a little fast. You say, well, you say application where? You have a broad range of application. Let me just tell you where you're going to apply it. Okay, first one, medical science, anything in motion. All right. First one is that you have this micro needle. You punch the skin. Use this electric field supply. You can stimulate the needle and enhance the medical performances here. So this transcutaneous electrical stimulation helps the recovery of a patient from pain relief and other things. This uses electric field generated by the tip. So this uses the TNG as a small power source. Just to rub a little bit, they give you a few hundred volts, and that's enough for this kind of purpose for that. So it's a self-powered microneedle. Okay. Secondly, is that you know when we work in the office, we always bend down writing things. So our neck suffers and the shoulder suffers, and we can do monitoring this one. You can monitor the whole thing, your physically, how you behavior, your body, your shoulders, your neck, everything. This will become a self-powered sensor for health recovery and health care, right? So a lot of things you can develop of it. As long as your motion, there's a signal. That's called sensor for that, right? And you can make this as a patch. 就是this 就是那个中医的药片儿。Chinese medication patch. You can make this breathable and wearable and also comfortable. You can put it on here. So if you rub it a little bit, the electric field generated can infiltrate the skin for a few centimeters, can deliver the drug 5 times as effective as you have no rubbling on the surfaces for that. So use this one for drug delivery for Chinese medication on the surface. Use the rubbling of the generated field. The other one is that you can have this patches put on different parts of your body for pain relief, for headache, for other things. Big help for that. So we have a lot of things developed on this one around for make the medication, use AI for medication, Chinese medication as well the medicine. So hopefully more digital data going to produce in the next few years or so. So this is called self-powered electronic skin for healthcare, right? And the second one, smart sports. Sports have a lot of movement, but sports have a lot of things to be monitored. Equipment for sports, training of athletics. This training of all kind of different athletics sports, also health recovery, motion. So this become a new field in smarter sports. All right. So as a result, TNG is naturally born for that. As long as you move, there's a signal that tell you how to recover over there. So we do this one for anything in motion. You ride a bicycle, you jogging, you kick a ball here, you swimming, and you playing this badminton, whatever you do. And this is one of the early work we published 6 years ago. Play ping pong ball. Is this a valid ball or is it invalid ball? Sometimes you have debate. I have debate. 1 point can differ, can be lose the championship. So basically, you can suit this one for the observation of the rules as well other content. So we developed this one into different universities. In China, there's several universities, especially in sports, right? Beijing 体育大学, Shanghai 体育大学, they have all this kind of sports program. So this is TENG for smart sports. You name it, as long as motion for that, okay? Then if you do ski, and you can monitor your, just prevent the head injury and measure the head injury. You make it into the this wearing head impact for that. You can use 3D printing and print this out with the mask for that. And with one, you can think of a lot of things, knee injuries or knee recovery for that. So all this is used TENG as a source for monitoring the sports. Okay, so this is for smart sports, and now is robotics. Okay, robotics have a lot of things. Robotic sensing. We use the 10 minutes left. Okay, this robotics, you can measure the use rotation TENG as a robotic. Then measure the angle change, everything change. Then this precision is one part. Is 1 part of 1,000th. That means what? Very small, a degree. So you can measure the robotics, the angle, and do the control. If you use the organic material for the angle control and the monitoring, the weight become lighter, much less power consumption, and life can extend the lifetime extensively. So you name it, anything move right here. Okay. So this is the robotics. Now is, if you look at this one, is particularly for the this have a audio. So is that is voice recognition.
Open Sesame.
This this voice can hear, and the person's talking.
Open Sesame.
Recognize voice. The second one is no talking, just the vibration of the throat. Can you identify what he or she? Oh, sorry. This is go back. Sorry, it's a little delay. Okay. Anyway, let me see if I can do that again. All right. Let's see. It's a little delay. All right. Okay. This thing.
Open Sesame.
The second one is just the throat vibration. We can use this.
Open Sesame.
How can we do that? This use AI assisted system here, so they can put the sensor on different skin part. So when you're talking, the muscle moves differently. Use this can reconstruct what he or she is talking about that, right? And this one can use if you use the artificial perception smart fingers, you can do materials identification. You not only can identify the shape, but also identify roughly what this type of this materials is, because 2 pairs between the hands and here, a pair of triboelectric pairs. For the charge characteristic, you can identify roughly what is this material. So give you hands a smart function. So this is called a smart hands. So not only we can make a robotic as a human, looks like a human, but more importantly, it can function as a human. So this as it knows the shape and the material type of specific objects. Okay, and furthermore, you can sense the temperature. If you have a sense the temperature, sense the material, you know how hot it is, how hard it is, and you can measure the force on the vertical and the sliding for that. Okay, so this is just the beginning of the robotics areas. The second one I'll talk about, this one is the crosstalk. So when you do the touching, you find when you touch the finger here, from pix to pix, they have crosstalk. So we did a special design by our colleagues. They minimize the crosstalk. So in between that, there's a gap. So have minimized, so have received the pressure measurement at a higher spatial resolution. And this helps for like catch the fingerprints and other things for that. So this is a touch sensor, use mechanical transducer, but at a high spatial resolution. So this is called minimized crosstalk on that. And furthermore, you can make a small. You can make a MEMS device as small as 50 micron, and the mechanical response frequency is 1 megahertz or so. So therefore, for MEMS, you do not have to apply a optical fiber or electric to measure the MEMS output. This gives you signal automatically. So if you think about, not only think about big, you also think about small, so you can integrate with microelectronics here, right? Okay. Smart fabric. Now we have many faculty at Hong Kong PolyU work on the fabric. Professor Shaw and others doing this fabric. Fabric is a big industry for that. And can you make fabric have some kind of functionality? Fabric is great for triboelectricity. So you be able to do this 3D wearing. Then you can contact the two different pi fibers. When sliding one against the other, the triboelectricity occurs. And you can make a smart sensor patch. You can make a smart jacket. As a result, if you use this one, you not only can have substantial power generation, not only as a sensor, but as a power generator. This is a small patch. It's only about 2 to 6 centimeters area, little smart patch. You're sliding on the surfaces. This is 1,000 LED lights flashing immediately. Okay, immediately. And if you have the commercial bubbles, each is 3 watt. If you're sliding a 3 by 6 little patch on surface, all this light can flash instantaneously as well. Of course, this can give you not only instantaneous power, but also can give you as a sensing, self-power sensing for that. So literally you can use any material for what you do, and this plays important part for the smart fiber, right? Okay, and this field is fast expanding, and there's many groups work on this one, and even we have a recent book on smart fabric use TNG and textiles, because smart fiber and fabric have broad applications from sports to daily wear, from the medical to a lot of infrastructure. These fibers, you have an enforced fiber for composite materials. All these things need kind of this. So this you have a broad range of application. I will not cover in that detail, just give you a flavor for that. Aviation. So if you fly, you always experience the turbulence. That's the this use for what? For course. You can simulate, but you need to measure. How do they measure? You can see this is a simulated cross-section of the aircraft wing. You can see the turbulence occurs. Let me show you how to. And then how do you observe that? They can use the fly of the strings on the surface of the aircraft. This is how do I monitor for that? It's non-digital, non-scientific, and not accurate. So we use TNG to fabricate this turbulence measurement system. Why we can do it is because the lift of the TNG give you the voltage. Voltage is the amplitude is lifting. The current give you the speed at which this is the lifting. So using this technology, you'll be able to drive to monitoring a lot of things, and this has now become even commercially viable for flying safety. Okay, and you can do big data analysis. You have a sensor across the wing. You can detect the local turbulence very precisely and do AI for measurements. You can provide a safe flight and controlling system for that. So I think this one, many people can work on this one, use this as a completely new sensor system for aviation. Okay, and also we have the collaborate. They work on this one, use UAV, because the materials make all the structures is very super integrated and very much functional design. Use the 3D printing for that. But inside the 3D printed materials here, how do you measure the shape change, twisting, other things? It requires sensors. So we built this one inside this composite materials. You can as you can see this kind of material here. You can measure the clapping of the two sheets and the compressions and all the things you can do the measurements. I just give you a flavor here, and you'll be able to read those papers in the details later, right? Okay. So this is for the aviation things. Okay, now it's civil engineering. You can, for what? You can measure the smart road. So when you're driving here, you can put on the floor, and the floor's vibrating, and you can do this one for the measuring, monitoring the floating here. So this is show you, okay? This is they put on floor here. If you're a car driver here, you can do a lot of monitoring of the condition of the road without additional power for that, because the car movement is a source of power. Either use the vibration or use the compression they provided locally. So this is use the smart road for safety monitoring. Particularly more, this can be used for what? The intelligent mining industry. You know, underground mining for coals, minerals, and other things. You can do this one for monitoring particular gases at the underground. That sometimes very dangerous for the miners to work on the ground. So you can use this, because any kind, you have airflow. The slowest floating air speed we can use is 0.3 meters per second. And that one can provide it such a breeze wind that be able to measure the local concentration of specific gases, use the power generated as a source of power. And I think this is important for a lot of cases that you do this one when you work in a complicated environment. If you visit some of the places that have the coal mining, it's very complicated on the ground, right? So this is for mining industry applications here. Agriculture, you can use for agriculture. And we find it interesting that if you apply electric field to the plants, its growth rate changes. As growth rate changes, and this is something turned out to be exciting field for smart agriculture. As you see, and you see, if when you apply, if you have no electric field, the heavy electric field, this is the magnetic field, you can see that the growth rate is different. So the electric field not only stimulated the biological system, but also stimulate plants. So therefore, this we have people, they are studying this one to try to enhance the growth rate for agriculture and also smart monitoring for that. So I just use a couple of slides to show you that. Now, I show you many things, but you say, is there anything commercialized? You say this is potential, that potential, a lot of potential. How many potential have you delivered, right? Okay, so we have some product I want to tell you. And also we have the companies registered just as starting. We encourage young people to be engaged. They start companies, so hopefully they can make, this is, you see, use the solar power pacemaker, right? This is used as the robotics for that. Many things started for that, but we just have a lot of opportunity to offer, okay? Now, let me show you, give you examples. Solar power pacemaker. We work on this one for 14, 13, 15 years. 5 years ago, for the first time, we make the pacemaker solar power. And we spent 11 years to do that. And this open door for implantable medical devices for that. As a result, the company is born as a result of this technology for that. So you can see this do open doors for the medical science. Keyboard, the type of keyboard. I know. Okay, the keyboard. If you make a keyboard to be not only recorded what you're typing, but the way you're typing. So when you punch those characteristics, they record the current and the signal. Big data can analyze the way you type. This can provide a new approach analyze a person's social behavior, the way he thinks or she thinks, dynamics. This one is also product scale. And furthermore, each family has a water meter for water measurement. How much water you use. We can use the floating water to measure the pH, flow rate, pressure, any kind of chemical change with water as one system. This one, each family is a unit, give you data. You can analyze the quality distribution of water across Hong Kong and other places. You can also apply the heating system in the northern part of China. They have the supply heating. Sometimes they have burst of the pipe. They don't know where it is. So you can measure this one, use big data analyze. Okay, here's the possibility the burst occurs. So this one is already transferred to industry. Use the floating water, you don't have to change the battery anymore. Give you data once a few minutes. Okay, so for infrastructure monitoring. Also for high power lines, we use this one to measure the vibration, the temperature, vibration, amplitude, frequency of the power lines. And this is already commercialized as well. We use this one to measure, use the power line vibration like that. You can do the monitoring at locally. So this is just the beginning of this power industry. Oh, I'm sorry. Okay, this is the one for vibration. Vibrations are everywhere. Big machines, trains, subways, anything. If you can monitor the vibration, amplitude as frequency, you offer a lot of things for safety of transportations as well as infrastructure for that. So if you can do that, so this already, we built this one for a few years and measure. You have to have a power harvester system that responds to a broad range of spectrum, not only just very narrow. If you use piezoelectric is too narrow. You only can respond to specific frequency. If you have broad frequency, use TNG is much better. Okay, much better. So, lastly, can this contribute to sustainability of humankind? Something big, not just small. And we work on the carbon neutralization projects. And according to this report from Chinese Chemical Sciences and European Chemical Sciences, they found they projected the future to solve the world, the problem for climate change is through the ocean energy to substitute fossil energy. This sounds a very ambitious goal. Is this possible? If possible, how? So ocean is such huge, it offers a lot of things. But the utilization efficiency is very low, very expensive, and very complicated. Especially near the coast of China, the wave amplitude is less than 1 meter on average. So it's low wave and come very slow, right? Such a low pace you cannot do very well with traditional technology, very expensive for that. So how do they do it? This is the accelerated play. This accelerated play use the wave to push. So this only in a place you have a wave push one side like that. If you're in the middle of the ocean, you cannot do it because the water is not going one way. They just randomly circulate. All right. So 10 years ago, more than 10 years ago, I was starting an idea. So when I wrote this article, I said, well, can we use TNG as an array to do this one? That time I said, oh, we can make a TNG ball inside the ball. We have my student, they are here. They did some of the early work on that. So is this possible? Can we put this one possible? So just as an idea. So we call this called blue energy because the water color in the ocean is blue. So we call blue energy to be distinguished from green energy. Okay, this is possible. So this was just an idea, 2014. And then because this wave from ocean is gravitation. It's there all the time. But we have to learn how to utilize that. So this is the idea at 2014. I wrote an article. Why we can do it, why traditional kind of technology is more difficult to do it. The reason is because at a low frequency, the response of ours is much higher than EMG. So you can have some power delivery. And also this device floating on the surfaces. So you don't sink on the surface. So the density is lower. So therefore it's floating on surfaces. So we want to make it not working. So after 10 years effort, we eventually make this one is 1 cubic meter area. And we reach more than 120 watt, up to 120 watt per cubic meter volume. And you think this is probably small, but for the conditions you think in the ocean, any random one, very hard to harvest energy from that one. So if you have a floating tank like that, any direction wobbling, we can do so, right? So this now is being tested in the ocean. See if we can we make this light tower so powered. Answers yes, we can do it, and we are testing. Let me see. You see, this is testing the real-time video. Let me see, will play or not. Okay. See this one, this real-time flame over there. And we already reach 200, up to 200 watt peak power from this one. So it's slowly working, but took 10 years to get today, right? But I think the future will be faster. From, you think about nano generation, look, all the people come to my institute, where's nano? Let me take a look, nano materials. Right, any grain nano can become big. Don't just say, the name was born because we was on next nano material, nano device, we call nano generate. But today you don't have to be small, right? This is the history of nano, right? So with this one, I think there's a lot of potential for the future as well. The covering scope is very broad. Let me see. Next one. Okay. How to solve the world energy problem? Not one technology can solve. So you can see wind, solar, and water all together, we call hybrid energy. So, okay, let's don't touch hybrid energy. Can we use this one? This is possible. So we work on with a company to do this on the ocean right now. So we hopefully offer comprehensive approach towards sustainability of energy for the future. You may think this is a long way to go. Yes, absolutely, because we are facing one of the most difficult questions, difficult challenge human face now, which is energy. You are solving the most difficult question we could ever face, right? So therefore, of course, take a long time, a resource, but I think we have a lot of talented young people for that. Okay, so summary. Today, I give you the base introduction, triboelectricity. Why? Number one. Number two, what's its impact to chemistry? What's its impact to physics? What's the impact to technology? What's the impact to commercial product? What's its impact to sustainability of humankind? There's a lot of things to be offered. I'm very happy to see a lot of groups in Hong Kong and other areas work on this one, because truly have things we don't know before, can offer things very exciting, not only academically, but more importantly, industrially. So I think this one can do. Today, I just give you a brief review of the work we did, and this has contributed thousands of our collaborators in the last 20 years. I will not name individual, and they contributed a lot of work to this one, our collaborators, graduate student, postdoc, and employees for that. Okay, before I run off, I need to run some advertisement. We have a new journal. Please contribute to us called Medical Mat. I'm the chief editor for. I was the chief editor for Nano Energy for 13 years. Now it's run. This is called Medical Materials, but also have another journal called Smart Sys. Smart Sys is a new journal for that. Do contribute a paper to us. And lastly, more advertisements. Books. We spent 5 years, total 14 volumes, both in the English and the Chinese here. The English books too expensive for students to purchase, but the Chinese version is much cheaper. Much cheaper for that. So I brought here this one. I show you this is the 4-volume TNG book. Give you all the fundamentals, techniques, and broad application and a range of things. And if you are interested let me see, in a technology application, this book is especially dedicated to technology for transportation, for mechanical, for civil engineering, whatever you are interested in, anything motion for that. And if you are working on fibers, here it's fibers for that, right? So fibers, that's a lot of things can do that. A lot of people, just when you do a different thing, they have a lot of expertise in different areas. I can only learn from them. But we can offer, what do we do? We can offer, what do we do? And lastly, I talk, let me see, there's one more, I think. One more. Okay, slow here. Okay, so if you are interested in the theory part, we have books published for that too. All right. Oops, sorry. That's one. So our team worked very hard on the last few years. We truly do that. We can help to establish the theory, fundamental science, and technology, and we also continue to do more experiment to validate the theory continuously. I think the more we do, the finer our theory is very valid and correct. Right? Okay. So let me go back to the summary slides, and the students already raised the board 10 times. I better stop for the things, okay? And okay, sorry, the conclusion slides. And happy to be at Hong Kong Polytechnic University again, and give me a distinguished honor to give this lecture. I hope we can reach a large audience, and your question and comments be very much appreciated. And also welcome you to visit our institute to continue to collaborate in many different areas. Thank you.
Okay, so it's my great honor to serve as the moderator for the Q&A section. So I'm Professor Xu Binggang from the School of Fashion Textiles. I and my team also do the research work on the term TNG and also energy harvesting. Yeah. Thank you. So I learned a lot. Personally, I learned a lot from this presentation lecture. I think all the audience here also learn a lot. So I think this is a very good opportunity so we can have the interaction with a world-leading scientist, Professor Wang. So actually we have two kinds of audience. First one is in the lecture room, and also we have online audience. So first we can start with the audience in the classroom, everybody. If you have any question or comments, we have many students here. Also we have the colleagues. Okay, thank you.
Thank you, Professor Wang, for a very outstanding presentation. Enjoyed it very much. So I have a question related to the blue energy. We're working on floating breakwaters to reduce the incoming waves, to protect the coast area, and to fully utilize the marine area as well. So I was wondering that this floating breakwater is quite long, a few hundred meters or up to a kilometer long. So I'm wondering that if the TNG technology can be used to generate large scale wave energy generator to be integrated with those such floating breakwaters. If yes, and what are the main challenges we need to deal with? Perhaps a room for collaboration in the future. Yeah.
Thank you. This is a great question. And it's also work on our future for energy tool here. Now we work on with the windmill, because when they build a windmill in the ocean, they use there's a pole here, and around the pole they have to build the infrastructure to protect it, because the wind continually strike on the pole, so they will not have a long lifetime. So now instead of put the around here is the protection layers, we can install our TNG there. They can absorb the wave and generate power. Then you and this one can protect the pole, also harvest the energy. And also, if you have the poles around, several poles here, you can build it around here, and the inside can for this farm, ocean farm, other application. Then you wonder how much energy we can generate, and you can calculate. This things is not just one layer. On the surface, we just say on the surface, but we can build 3D, 1, 2, 3, 4. Depends the activation of the water below. You can make a string of them. And when the wave strike here, the things will be just floating like that. And the TNG array responds to the wave here. So our roughly theoretical calculation shows can deliver substantial power. Let give you a number. The Three Gorge Dam, 就是三峡大坝, the surface area. If you use surface area, 1 meter of depth water, the total power generated is more than what Three Gorge Dam can generate per year. Just based on very conservative estimation. So now it's just we need to make a model system for that. We can scale up, just like a solar panel. You make a one wafer, then have a panel, and then panel of panel is a farm. So you can deliver to the world energy that. So we're doing step by step. We're still at the early phase, need the resources, I need the people to work on that. But I do believe we'll be able to achieve the goal.
Okay, I think
this also can be worked on not only on the coast area, in the ocean, because it's floating. So that as long as this network will not float away, you're fine. And it can blow the water too. Yeah.
Okay, Professor Wang, so the blue energy is one of the most practical scale-up method for the TEN application, right?
Okay. Yeah,
Yeah.
we hope, yeah, it's because this idea is a brand new idea to do. And we also show it works, and future is how we're gonna make, how much power generated. I think it depends. Many scientists, engineers work on that to make it possible. But I think from estimation, theory estimation is possible.
Yeah, thank you. So any questions from the audience? So before you ask question, please let us know your name. Okay.
Hello, Professor Wang. I'm from the PolyU Civil and Environmental Engineering. My name is Wang Jiamei. For my research topic about the TEN, I have some question about the materials durability, because for my study, I didn't use some surface treatment, such as we often use in materials lab. So I just use the simple FEP film, some like the copper film, and I cannot generate the enough power as papers you published. So I wonder, is that the problem of the surface treatment? Another thing is that durability, because the different environments such as the humidity, temperature will affect the performance. And another thing you mentioned that the comparison between the EMG and the TNG, I think the EMG is a simple structure, have been studied maybe 20 or 3 years ago, but I think the output of the EMG often performs stable. I mean, it's a simple but stable as a output. But for 10 TNG units, with a time, with several tests, I found it will decrease the electronic output. So that is my problems.
Okay.
Thank you.
Okay, good question. Let me first ask you the durability. Durability is that when we first studied this one, we found how do we improve durability? Later on, we found several approach. Number one is that you need the operation mode. You see, for example, you don't do this rubbling all the time, because when the charge build up on the bottom here, it lasts for hours. You don't have to do this. Only do this 5 times, 3 times, it's the fully charged. If you continue this, there's no more use. So we build the mode is that after a few times, it's lift up a little bit. So then just sliding back and forth. There's no contact. So this is the operation mode conjunction, number one. Number two is rolling mode. So not just like that, we do rolling mode. So this rolling mode can much reduce the wearing of the material. That's number two. Number three is that lubrication. This is found by surprise. When I talk to the people in the tribologists, they say, well, can you put some oils there? I said, no, this won't work. From my first instantaneous response, they said, well, let's try it. So put in some low dielectric oils. It's not only preserve the performance, it's not reduce the wearing, but also increase the performance. I was very much surprised by that. So you can, a 3-way you can do that. You can improve the robustness for that. That's your first question. Second is temperature. Temperature. The highest temperature you can work is probably like 300 degrees C or so. For polymaterials, you have to be below 200 degrees C. And for the coldest temperature, the colder the better, because the charge preservation is excellent at low temperature. And we did the test on the liquid nitrogen temperature, and it works well there too. So the temperature low is not an issue. The third question is about the stability. Stability is that to say, compared with electromagnetic generator, it's electromagnetic is more stable than us. This involves materials improvement, because EMG has been around for almost 200 years. So all the things are very well established. They have many optimizations. So we are still in the process to improve the durability and the performance, but now still in some areas that can be applied, especially for sensors. You know, when you have a movement, the output voltage is really high. For sensing application, it immediately can be utilized for that. So you try to utilize in the way you can use right now, then the other aspect will be continued improved as more people devote energy and resource on that. I believe so. Yeah.
Okay, thank you. So if you still have some questions about the details of experiments, you can also
Yeah,
discuss
the details.
with your professor
Yeah.
and also other teams in the PolyU.
Yeah, these,
and my team, okay?
Yeah, the measurement can be the measurement can be the way you fabricate devices, the size, and also the measurement equipment you utilize depends. So this has to look at case by case.
Okay, thank you. Any more questions? Yeah.
It's it inspired me very much. I just have humble suggestion. We are scientists. Scientists is answering why. You have find many rules. Science is rules, or science is truth. You have find many truths, answering why. And the second is how, because science is for the betterment of human. Then you must how to implement it. I just have some very humble suggestion because I have similar experience. I've written a book several years by elsewhere, and last month was in the 中国 in the 中国科技会堂. My favorite is 4N 4F, the integration of energy, transportation, information, and humanity. My humble experience is first, you have get the support from the government. There's four sectors: policy, industry, market, and investment. My own humble experience is you must have partner with big industry. In China, 央企还有很有实力的民企 because they have, once you give the idea to them, they can implement, they can invest, they can have key project, turnkey project, and implement. So for instance, in your area, I think very useful is 国网、南网，还有两个，一个是能建跟电建。particular 不知道你有没有联系这个中能建国州吧？我认为中能很适合你这个很多东西，他们可以实现的。一个是中能建，一个是中电建 ，because they can have a project. This is my humble view, and I wish to close connection with you because this is for China and for the world, for the global sustainable development.
Thank you. This is truly an excellent suggestion. In fact, we are working with them. We have some projects going on right now, 中能建 and the other ones. They are the one have the application field. So, and we starting to discuss and implement some of the technology, but it's in a slow process. Sometimes just feel my own capabilities not strong enough to drive that. Yeah, you can help us to introduce it. Yeah, 中能建, yeah. Thank you. Excellent suggestion.
Okay, thank you for your comment and suggestion. Okay.
Hello, I'm from the SFT department, and my name is Quentin Zhao. And you have talked an interesting topic that you discussed. You can transfer the high entropy energy into usable energy. But based on the theory, the energy will not come from the disordered trend to the ordered direction. That is my question. How could you make the disordered energy into usable energy? Thank you.
Very good question. There's energy generation is one part. So generation is one part, utilization is the other end. Okay, so you generate, this can give you irregular energy, but must have energy storage units follow which. So the power you generate, you store it, and then when you utilize that, can be regulated energy. So have three parts: power generation, power management, power storage, and utilization. So all this come together as a package.
Yes, yes, I agree. Okay. Any more questions? Especially the students doing the similar research in this area.
Professor Wang and Jason, I'm a recent graduate. In my last year's school course project, I've done something related to TNG. So I searched online about the current commercialization status of this technology. And it seems that it's still in a very early phase of commercialization and there isn't much information online, maybe except for the Zhongke Daqing or something. So I wonder if you can share more about the commercialization status of TNG now and also maybe your maybe projection or forecast in like 5 years or so. Thank you.
Good question for that. This is basically commercialization is started in various countries. And I know that in Korea, there's several companies started on that. And also the early days, they have a Samsung company have this project internally for that. And for us, we have started about a few companies right now. And also outside of us, in many other campuses, there are young people starting, but still at an early phase. Recently was a group of young people on the vibration energy harvesting application. So as you're right, it's an early stage. There's an opportunity there, and there's gonna take a while to get mature, and that's why we need to get on as early as possible, so you can take a first foot on whatever the market need and what you can offer for that. So anything just like energy technology take a long time to reach some kind of application. I just use one example, the solar cells. The first fingernail size solar cell was 1954 by Bell Lab, and 1954 until 1977. That time generated 1 watt, 1 kilowatt hour, 1度电, 1 kilowatt hour, $77 that time. Very expensive at that time. No commercial opportunity at all. Right? By year 2000, they continued to drop $6, $6 for per kilowatt hour. Still expensive. But today, as the industry dry, a few cents probably per kilowatt hour. So this need many resources to devote in materials issue, interconnect issue, all the optimization. So I think if the society have a need for that, definitely they will be drive this toward this direction. So we're still at the early phase, so that we face a lot of unanswered questions for that. Then this means opportunity. So I hope for you through that one, you can capture this is what I need to do, and maybe 5 years you can do something very completely different.
Okay, Professor Wang, can I supplement the answers?
Yeah.
I provide my understanding of this question. So about the application commercialization, so Professor Wang's lecture mentioned about high energy, right? So if we actually, the term, my understanding is has advantage for the distributed energy. Yes, and then for the distributed energy, this is really pioneering research in this area. Not only we need to generate the small energy, but also we need to utilize energy. That is not only the work in energy harvesting, but also power management, especially macro electronics.
Exactly.
And also the other areas together. So I think it will take some time to stronger grow up. Okay.
Yeah.
Okay, thank you. So yes, okay. So any questions? Any more questions, everybody? Okay, Professor. Yeah.
I'm Chang Zhu from EEE department. My question is, it's a very stimulating lecture. I really enjoy it and open a lot of my mind, I know. And what I'm interested to know is, can you talk about anything, the challenge and the weakness and the problems with this technology.
Yeah, thank you. Many change depends which part of it. So first one is the materials optimization. How to make materials robust, last longer, better delivery of the charge. So number one. Number two is the design of the system. So if you make a patch that large, no good. You have to make many small patches because you have to maximize the leakage of the current, then you get the best output. But if you have too sparsy, that means the total power will be lower. So that you have optimization, system optimization. Number three, we have to be package the thing. You can't expose this to the air. You have to package the system. Number four is that power management and storage as integrated. So give you is a pack. So now we try to make a module. So when I give you a module, this module have every part there. So you need just this is the output and this is the two lead. You just integrate as what you need for that. So just like a battery, give you a standard unit. So that's what we try to do right now. So many challenges faced now from materials and also the engineering part for that. So it's just at a very, I think it's at early phase. Early phase. Thank you.
Okay, thank you. Any more questions? Okay, if we have no question, I will ask some question from the online registrant and also online audience. So I have an iPad, so I can receive the question from the audience. Okay. So I will select some of the questions. Okay, relevant. So first one, I'd like to ask how long it will be before we can use triboelectric generators and make them widespread in our daily life. Similar questions.
Similar question.
Yeah.
I anticipate 3 to 5 years we have some truly product available. But if you want over broad application daily life, I think it will take 7 to 10 years to get there. And but at least in the next 3 to 5 years, we should see something coming. That's one of our expectation.
Yeah, it's okay. So there is a very specific question. Can TEN be used underwater on the deep sea seabed?
No. In principle, you can because the whole thing is packaged for that. You can. It depends on the seabed. That it depends the magnitude, the wave, it moves. Compared to the surface, the energy harvesting efficiency would be a lot lower. But I think it should work there.
Should be workable.
Yeah.
Okay. Thank you. Another question is, how can biomedical nanomachines implanted in the body prevent interference between the power generation and the body's internal neutral electrical signals, especially in heart and brain?
Good question.
Yeah.
I think these basically they work on different mechanisms and also principles. So I think from the design itself, there will be no interference between the two.
Yeah. Okay. So, this is a different kind of question. How to keep the enthusiastic and creative during a long academic career? It's a general question.
General question. This is to answer this question. I would say first one, to be creative over long term, you have to really love science. You have to have a passion in science, because just like when I was 20, 30 years ago, you publish a great paper, people say, "Oh, great! How can you continue to do it?" That's always a challenge for everybody. So I think the answer is that keep curiosity, keep working, keep excited, and keep positive about what you do, because whenever you do, there are always people possibly question you, don't believe in you, and build own self-confidence is most critical to overcome those difficulties. And I think be excited with what you do, be passionate, and always have a confidence that what we do, we will change the world in the future.
Thank you. This is a good good answers. So I think the other questions are very similar. We discussed already,
Yeah.
so we can skip. So I want to ask you the last question for the students, for example, here. So for example, some students are doing research in TEN, or some students are doing related research. So as the world leading scientist, so can you give a piece of advice on the research on TEN, for example, directions, applications, whatever? Can you give a piece of advice to all the students?
First, I'd like to thank those students and work on a project because this is new and exciting. My suggestion is that fix your goal. This is the area I want to work on. I want to be the very best one in this one in the world. And want to solve this problem, and then I can commercialize a company or produce some product. Really, people eventually can utilize that. Not only publish the high impact scientific papers, but also sometime in the future, people can utilize this one. So I think I personally believe you are in the right field and compare with today's competitive field among different areas. This is new and also a lot of things can offer. And there's no limit for what you can do. There also always have the potential for you to explore your own creativity and the prosperity for the future.
Okay, thank you very much.
Yeah.
So that's all for the Q&A session. Okay, thank you.
Thank you.
Professor Wang. Thank you. Thank you a lot.
Professor Wang, you have done a very great job. And you probably noticed that today we have a full house of our audience here. And more than that, I believe online there may be more than 20,000 audience as well. So to express our appreciation, we make this special souvenir for you with your name and the title of your presentation, etc. So thank you very much. Thank you. And now I think this lecture is adjourned. And please, keep tuning on the future announcement from PAIR. We often have these distinguished lectures every month. Thank you very much.